All right, recording is rolling. So it is Monday, October 31st. That is Halloween day. We're starting off a new week here. And so I got some top scientists for you guys. Top scientists. Oh yeah, look at you guys go. So go up there then. Good job on centripetal force, gravity, and orbits. Oh, by the way, I have returned your quizzes and everything that you guys have done up to the last weekend. I'm going to set you guys up with a lab activity at the last 20 minutes of class today. So that'll be a good opportunity to get your quizzes back if you want them. Okay. All right, but we are continuing with conservation of energy. That's what we were doing last week. Conservation of energy. So here's some activities lined up. Okay, so we did top scientists. I got the starter question for you guys right here. Throw a ball up at some speed. How high does it go? So you guys been thinking about that for a few minutes. This 3-page table, we're going to knock out a couple more rows. Okay, won't quite finish it, but we'll get closer. Okay, and then the last 20 minutes of class, set you guys up with those pendulum activity. Okay, so that is the agenda. All right, how about now? Did anybody figure out by now? If you throw the ball straight at 30 meters per second, how high does it go? Okay. So let me take you guys through a few different methods of solving it, because by the time by this point in class, you guys do have a few different methods. Right. One method. So let me go way back in the day to kinematic motion. You guys remember kinematic motion? Well, let's count second by second. We'll go through the story. We'll just do it like right. So if you throw the ball up at 30 meters per second, then how fast is it going after 1 second? 20 meters per second, right? Doesn't it lose 10 meters per second every second? As long as you're on Earth, right? Then so now it's 20 meters per second. Here how fast it's going up. 10 meters per second. Here how fast? 0. So that would be the peak, right? If you throw it straight up. So it take 3 seconds. 3 seconds to reach the peak. Hey, would it also take 1, 2, 3 seconds to crash back down to the ground? Okay. Right. If you go to the edge of a cliff and you drop a ball, how far does it fall in those 3 seconds? Tick, tick, tick. So you could say the height change is 1/2 gt squared. You guys remember the Paul Hewitt story with walking? There's an old mine shaft. It takes 5 seconds for the ball to reach the ground. 5 times 5 times half of 10. It's about 125 meters deep. How'd you know that? College. You guys remember that? Okay. Hey, this is that, except it's for 3 seconds of falling instead of 5. So we're going to say the height that it fell is, well, let's see, we're assuming we're on Earth. That's 10 meters per second squared. You have to know what planet you're on to get an answer. We're going 3 seconds of falling. You got to square this 3 seconds. That feeds them 3 right there. 3 squared, it's 9. 9 half 10 is 5. 9 times 5. Oh, 45 meters. 45 meters high that thing goes. Okay, 45 meters. You guys get that? Okay. Or tell you what, there's a way you could solve with kinematic equations that you didn't even have to get 3 seconds, although obviously it takes 3 seconds up, 3 seconds down. But you could cut straight through that by applying this third kinematic formula right here. It would actually be a more direct way to get it. Because you say, well, I know how fast I threw it up. That's 30 meters per second. That goes there. At the maximum height, it happens to have reached 0 meters per second for final speed. Okay, so that could mark its maximum height. And you know that gravity is pulling down at 10 meters per second squared. So you're solving for displacement, which in this case is like a maximum height. So from the perspective of that equation, it will look more like this. Final velocity squared equals initial velocity squared plus 2ax. Then this number goes to 0. Squared equals, I threw it at 30 meters per second, straight upward. Got to square that. Plus 2 times. Now, if you throw it upwards and gravity's pulling down, I better actually plug in -10 here. -10 meters per second squared. And then this x, well, that's going to represent h max. I'll just call it h, but it's like the maximum height that it goes to, right? That's what is 30 squared. Is that 900? Right? Can I subtract 900 over? Say -900. And the unit also gets squared. So meters squared per second squared is equal to, say, -20 meters per second squared times the maximum height. Okay. Is it okay? So 30 squared is 900, subtracted that over. So it just looks like that, right? Okay. 2 times 10 is 20. Okay. Then if you want to isolate h, can you divide both sides by this -20 meters per second squared? So the height, maximum height, would be -900 meters squared per second squared divided by -20 meters per second squared. Okay. 45 and the unit is meter. That's the same thing. That's the same thing we got by counting second by second. Okay. Falls 45 meters in 3 seconds, or using this approach, it rises to a height of 45 meters. Same thing. Right? But you know what? Since we're doing all this conservation of energy stuff, right, now we have a completely new framework for approaching the same code. Of course, it should lead to the same answer if it's also a valid approach, which is to do conservation of energy. Now, if I want to do conservation of energy for a closed system, let's make sure we got everything in order here. What objects are in the closed system? And the ball goes up and comes back down. What objects are in this closed system? The what and the what? The ball, of course, but also I have to consider the earth. Because the earth is like pulling on the ball. It would be an external force if we don't internalize it in the closed system. Yeah. So the ball's like the earth is doing work on the ball. So I've got a ball earth system. I'm going to say that the sum of energy initial is equal to the sum of energy final. Okay. Haven't you guys seen this step as the first step over and over and over, all over in your notes last week? To set up every single one of these that we did last week. Okay, is that true? Okay, so here's the ball, like right after it's left your hand, we're going to call that like height 0, basically. It's right near the ground. Okay. So this ball moving really fast, but has no height, means it has all what type of energy?
Kinetic.
Kinetic. Do you guys remember what the expression for kinetic is? Might be on a poster hanging from the ceiling. 1/2 what? mv squared. 1/2 mv squared. There you go. Right. Where the speed is like the throwing speed. Of course, it throw a little knot on it, right? Okay. It starts slowing down, but right. That was the initial speed. Right. So it's a speed at that point. Right. Then we need to pick a second location. So this is like our point A right here, point A. But here's our point B because we want to figure out what's the height at here. And at the very top, it has no more speed if you go like straight up. Okay? But it does have height, which means it has what type of energy? Potential energy. What's the expression for that? MGH. Okay. And the question is, what is this height? This really represents the maximum height, doesn't it? Okay. Ooh, this setup sure does remind me sort of the Galileo setup, except Galileo was backwards. Galileo started on top of the tower and dropped the ball, and there was like some crash speed. But look for some of this. You know what? Let's solve this in terms of variables, which I don't like to do very often with you guys, but notice I never gave you the mass of the ball, but that's okay because the mass cancels out anyway. I mean, that kinematic stuff, we never even considered the mass of the ball. Here, the mass just cancels out. So that's, if you think it's really confusing, you could always just make up a number and plug it in. Like you could say you have a 1 kilogram ball, just check those straight up or something. All right. So solving in terms of variables, do you see that there's only one step anyway, which is just divide this G down? You guys see that? So this H is equal to, right, I got the throwing speed squared. I'm dividing this 2, and I'm also taking this G and dividing the G down. So look like this. Okay. Now I have a general expression, which I can figure out the height of any ball thrown at any speed. And in fact, I can even switch planets. Yeah, like that, right? Right. Yeah, you guys see that? Okay. You know what might be a little bit more practical application of this? Is suppose you and your friend are set up and you throw a ball straight up and your friend is like on top of a like 5-story building or something. And so it's like, how high does the ball go? Okay. If you measure the height, measure this H, do you think you could back calculate what the throwing speed was? Ooh, I bet you can do that too. Right? That's not where we're going with this problem, but that's very similar setup. All right, but let's plug the numbers in because you guys already know what the answer to this question is. It's got to be 45 meters. Let's see if this method if it pans out. So if I throw it straight upwards at 30 meters per second, I square that. Divided by 2 times Earth gravity, 10 meters per second squared. Okay. So isn't that like 900 meters squared per second squared, all divided by 20 meters per second squared? Oh, that's 45 meters. Boom. Same thing again. Okay, so there you go. There's 3 different ways of doing it. And the last way we did it is the theme of last week and this week, conservation of energy. But it leads the same answer regardless of how you approach it. 45 meters. Okay. All right, guys good there? That's a pretty good warm-up. Coming to this Monday. Okay. So let's go to this 3-page table. Okay. So got all these conservation of energy setups. We've done most of these. Okay. Today, I just want to knock out these two, and I'm going to save the asteroids for a different day, okay? Because there's more I want to say about the asteroids. Right. But the last one we did actually is a good review because it's very similar to this next one we're about to do. Right. Last one we did, last one you guys saw back last week was you take some mass, right, you smash it down into a spring, smash it. The force that takes is equal to k times x, but the energy stored is 1/2 kx squared. That's what we care about here. So different equations related to springs. Notice you're talking about a force or an energy. Here it's an energy. Okay. Now let's think of how it's gonna shoot straight up. Okay. How high does it go? Well, you know, the point has all gravitational potential energy. You can set those equal to each other because the ball spring Earth system is a closed system. Then you can solve for stuff. Some interesting questions might be like, if you know how high it goes and what the mass of the ball or the cartridge is, then and also how much you smash the spring, how much you compress the turbine, you could calculate how stiff the spring is, right? Or if you knew any other set of variables, you could solve for any other thing that was unknown, right? The question here is just the universal question on this table: what's the speed at point B, which in this case is 0 meters per second? Maybe not the most exciting question, but could be able to answer something like that. Right. But the next scenario is very similar. But instead of a ball being sprung from the spring, now I've got a block falling onto a spring. It's just like the first problem in reverse, isn't it? Right. So it's kind of the same object. I don't know why I just walked off the ball for a block, but I have a block. So let's call it a block. I care about the Earth because there's a height change. So the Earth's gravity is doing some work on this block that's falling. And of course, the spring, because the energy ends up going into the spring. Right? Guys, what kind of energy at point A? Isn't it all mgh, right? And suppose at point B, now we're gonna make a reasonable assumption. Suppose the spring is like maximally smashed at point B. Okay. What kind of energy at point B? Is it all 1/2 kx squared? Right? Isn't that just the reverse of the last one I said? Right. You can set those equal to each other, and again, solve for stuff. Right? Now, let me add on a little bit more to start, because when I was setting up this table for you guys, I really wanted to keep this like forest for the trees, like big picture, what's going on. But you know, if you wanted to get more into the details, you can say, well, I could add the story by like, if I roll the clock forward, maybe the spring is gonna boing, like rebound the block from it. So there could be more to the story, right? So these are just two very specific points. This is the maximal compression, which is different from the equilibrium compression. Like if I just take a weight and I just like rest it on top of a spring, it'd be different from if I drop it. This is like the dropping compression. Another detail, if you're thinking really carefully about the details here, you might say, hang on a minute, that vertical compression, is that also included in the height fall? Right? Which it would be, because after this block hits the spring and starts smashing it, Earth's gravity is still pulling it down. So this X is still included in this H. Right? So if you come across that one day. Right? But let's just go ahead and knock out this question and then move on. What is the speed at point B then? Yeah, again, 0 meters per second. As long as the spring is maximally compressed. Okay. Of course, that's only true for one instant, and then the spring's probably going to rebound it. But that aside. Right. Questions so far? Okay, so let's knock out one more of these for today anyway. So I've got a ball rolling down an incline. Now, this scenario you guys have not seen yet. Actually, it's going to involve, sorry about that, let me get stuck on here. Okay. It's going to involve physics that we're going to get to either in December or January, depending on how the class plays out. Rotational mechanics. All right, on here we go. Okay. Rotational mechanics. Okay. But at least want to set this up with you guys so you can think ahead a few weeks. So if there's a ball rolling down the incline, do you think you care about the ball? Care about the ball? Right. The fact that there's a height change means you must also include the Earth. So I've got like a ball Earth system, but I'm going to include one more thing. Okay. Rolling. The only reason it rolls is because there's friction. If there was no friction, it wouldn't actually roll. If this was like a frictionless tabletop, like air hockey table, right? You just like tilted it up, it wouldn't actually roll. It would just slide down, which would look really weird. But the fact that it's rolling, I'm going to also include the surface of the incline itself. Okay. Now, this friction will act differently than the friction in the open systems. Like before, we were looking at examples of like a kid slides down the incline or a car breaks to a stop. Both of those involve friction, but I was calling those open systems. Like there was work being taken out of those systems, right? But this here in this example, friction is more acting as a conservative force. So if I had another incline up here, the ball could just go shoo, 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 shoo. You could do this all day, and it wouldn't be taking energy out of this closed system. Okay? So this friction just induces rolling. Okay, so what type of energy at point A? Yeah, gravitational potential. A lot like this one, right? Gravitational potential. So I'll call it mgh, throw a little subscript A on that H. Okay. How about by the time you get to the bottom of the incline? Now here's going to be a mix of energy, but what's one type of energy, do you think? You guys think it's moving? With so probably 1/2 mv squared. Okay, so that's kinetic energy, but I'm going to specify a little bit more. I'm going to call it translational kinetic. So if you point a radar gun at the ball right here, it's going to read a speed versus ball has mass. You can calculate how much kinetic energy. But you know what? Some of the energy also goes into making it rotate. Now here's where, do you guys think if there was like a solid bowling ball up here next to a hollow basketball, next to like a solid cylinder like the sky, and it was like a 3-object race, that those 3 objects would reach the bottom at different times, they would also have different speeds? They sure would, because the mass is distributed differently, so they all roll differently. Right? That basketball turns out it's really hard to get it rolling. The bowling ball, it's really easy to get rolling. Right? So again, that's a future topic, but here's where we're going with this. I'm going to say plus, right? And I also need like energy of rotating. It's called rotational kinetic energy. So that's 1/2 I omega squared. Okay? Now, part of this you guys are familiar with, and part of it you haven't seen yet. Right? This omega is related to this V, and you guys know that. In fact, it's that poster hanging up there on the right on that wall. Right? You guys know that either V is equal to omega divided by R, or omega is equal. No, sorry, scratch that. Back up. Either V is equal to omega times R, or omega is equal to V divided by R. Right? You guys remember that? Right? Talk about that a little bit. And that I has to do with how the mass is distributed in the object. It's called rotational inertia. Right? So a basketball would have a lot of rotational inertia. A bowling ball, less. Well, you know, for equal masses, right? Just right. So those objects roll differently. Okay, let's not worry about solving this today, but in the future, you guys will probably be able to. But that's the big picture setup. Okay, and the asteroids are going to save for a different day. Okay, you guys good on this? All right. All right, so hold on to this packet. We'll make a return trip down the line. Okay, and now we're going to the last activity today. So I think I gave everybody one of these. Does anybody not have this page? Everybody get this page? Okay. Now this page has 3 different things going on with it. So on the back side are 20 conceptual questions related to energy, which are also posted to Google Classroom. Right? And my plan tomorrow is to go over these with you guys, to go over the conceptual questions. And then by the end of this week, I'll get you guys your next quiz. And many of the quiz questions are right here on this page. You guys got that? Okay, so you guys know we're going over all the answers to these tomorrow. And many of the quiz questions are these questions. You guys got that? Right. So the other side here, I've got 2 labs set up for you guys. Right. Let's take a quick look at the one that we're going to save for Wednesday. Right, just to get that, knock that one out of the way. Okay. Guys remember those ball launchers that we're using to do a projectile lab a few weeks back? Okay. So we're going to break those out again. Okay. And we're going to do a very similar lab to what you guys did a few weeks ago with the projectiles, except we're going to do one more step. You guys remember that these ball launchers had a spring in them? Yeah, smash a spring. Right? You guys remember that? To launch it? Ooh, I bet there's some spring constant of that spring. And I bet you could calculate it. And one of the steps would involve conservation of energy. So this is going to be Wednesday's adventure. We'll head back out to the balcony, we'll shoot off some projectiles, and we'll come back and crunch some numbers to figure out how stiff is that spring. And obviously, the more stiff the spring, the further it's going to go. Right? So if you know where it lands, you can calculate the spring constant. Right? All right, so we're saving that for Wednesday. Here's what we're doing today. We're going to be doing, you can see a little pendulum setup. Let me blow up that picture and set this up with you guys. You guys, what are we trying to get here? So we get a vertical line. All right. So I got a pendulum. Pull this pendulum back. Ball right there. Ball right there. All right. And of course, this pendulum is following like part of a path of a circle, right? Like a curved path. That's into like a circle. Okay. And there's going to be some height change from where you pull it back to its lowest point. Right? And that height change will be important because, well, about to set up some kind of conservation of energy, right? Okay. So this ball has some mass m, label that m for mass. Okay. This pendulum is going to have some length L. I bet you could pull out a meter stick and measure that L. Okay. And you can pull this pendulum back some angle theta from the vertical. You guys have some protractors, you can measure that angle theta. You guys remember how to measure angle theta, right? You're going to take the node of the protractor, which is like this point here. Someone will have like a little T or a little cross right there. Right? Park it right there. Zero out the vertical. See how I just zeroed out the vertical? Right? You guys are going to be doing this here in about 5 minutes. Right? And it looks like this sweeps through 36 degrees. Do you guys see 36 degrees? Right? In fact, that looks about 36-degree angle. I could leave that 36 degrees. You guys see that? Right. Everybody good? Everybody know how to use the protractor? All right. All right. So, is this ball gonna have a pretty big speed down here? Probably its maximum speed. I'm gonna call that V. Right? V for velocity, like speed, velocity. Okay. And that actually would be the maximum speed, wouldn't it? Because guys, at this point, the ball has all what type of energy? Potential energy. And here, if you define this as height 0 at the bottom, lowest point of go, but it has motion, means it has all what type of energy? Kinetic. You think the potential energy here is equal to the kinetic energy here? That's going to be the set we're going to use to figure this out, right? So I wonder what the speed is based on this L and this theta, and of course, whatever gravity field you're in. Okay? And it has something to do with this height change. I'll call this H. H for height. Like from here to here could be a height change, right? Okay. All right. Let's go through this together. This is a little bit tricky geometry, but this will make sense. Right? If you think deeply about this, then I'll give you guys an expression. You can just plug some numbers into. Okay. Okay. Do you guys see that this L and this L is the same L? You guys see that? That's the same length, right? Okay. So if I want this height change, could it be the full length of the pendulum minus this leg of this right triangle? Do you see that? Right? So here's the full length of the pendulum. Here's a leg of a right triangle. And if I take the difference, L minus this leg, that should give me H. You see that? Right? So if I want to figure out the height change, well, first I have to figure out what is this leg of this right triangle. Right? Well, that kicks way back to like, what, first or second week in this class. Okay? And what is that equal to? In terms of L and theta, it's what times what? L times the sine or cosine. See, it's adjacent. Means it must be cosine of the angle. Okay. So if it's like 36 degrees, and suppose you have a length of like 1 meter, take 1 meter times cosine of 36 degrees. Okay. Okay. Now that's what that's equal to, right? But this height, isn't this height the difference between L and L cosine theta? Right? Is that true? Okay. And if you want to be a bit fancy about it, there's a reason I left a little bit of a gap right here. I could say this. I could say H is equal to. Okay. I've got the difference between two terms. They both have the L, so I could factor the L out. It's not 100% necessary, but you could. And then do 1 minus cosine theta. Just like that. Okay. Now you can figure out for a pendulum the height change based on the length of the pendulum and the starting angle from the vertical. You guys can do that? Okay. But the point of this lab is to figure out what is this speed V. Okay? And you're going to approach this from two different points of view. One point of view is going to be this calculation. And the other point of view is you're going to take one of these speed gates, you're going to dunk it upside down, let the mass go through, and you're going to directly read the speed, which is going to give you an empirical value. Right? So the calculated value and an empirical value, I bet they're going to be the same. Right? So let's figure out how would you do the calculated value. So let's do sum of energy initial equals sum of energy final. Right? Got conservation of energy going on. You guys told me it's all potential energy here. That's your MGH. And you guys also told me it's all kinetic here. That's 1/2 mv squared. Of course, this v is the maximum speed, so it's at the bottom, right? Ooh, do you guys see that the mass of the pendulum is going to cancel out? Okay. Yeah, if you think it's confusing, you just plug in whatever mass value, but it doesn't matter what it is, it's canceled out anyway. Okay. We're solving for this V. right? Let's solve this in terms of variables because we're just like, we're so close to doing it. Right? Can I see I can cross multiply the two and get v squared is equal to 2gh. And then I can take the square root and get v is equal to the square root of 2gh. Hang on a minute. Where have I seen that before? I see this all over the place, including the Galileo problem. Look, Galileo drops the ball. This energy at the top, this energy at the bottom. What's the speed at the bottom? Square root 2gh. That's what it was last week. That's what it was in the distant past in this class. That's what it is for the pendulum today. Guess that? Okay. But we're going to throw in one more tricky step because you guys remember we have h not as a measure value because I mean I guess you could sort of like hold up a meter stick here and kind of figure out what the height change is, but that's kind of hard to do. Okay? A better way to do it is to calculate it based on this L and this theta, which are much easier to measure, and feed that in right there. Okay. So here's your final expression. V is equal to, I got a big old square root. I got a 2 in here. I got a G at 9.8 meters per second squared. And then in the place of H, I'm going to write this expression, L times 1 minus cosine of the angle. Big old square root right there. Okay. So that is the calculated speed based on gravity field of the planet, the length of the pendulum, and the starting angle from the vertical. Okay. You should be able to calculate the speed in principle. Okay. Guess that. Okay. Now, let's go to this table that you guys are working on today. Okay. So I've got a tiny picture of this pendulum. Right. Let's go left to right. What trial is this? Let's see if you can fit in 3 trials. I think we got time for, let's say, trial A, B, C. Okay. Gravity field. Guys, what's the units for gravity field? It could be meters per second squared. Okay. Let's go 9.8 today. We'll use the precise value, 9.8 meters per second squared. Okay, that'll be true all the way down for stuck on the surface of Earth. Okay. Length. Now, if you're using base SI units, that would be meter. Length could be a meter. Okay. If you look at some of those pendulums back in the lab areas from last class, did they look about 60 centimeters long? About 60 centimeters, do you guys think? Okay. So, guys, would you, suppose you get one that's exactly 60 centimeters. Would you write the number 60 here? 60. I see you guys shaking your head. You guys are right, you would not. That would be, guys, 60 meters would be like the height of a very tall building. Okay? You don't want 60 meters. You want how many meters? 0.60. So this would be 0.60, right? Kind of like if you have 60 pennies and they say how many dollars you have, you say, oh, well, that's 60 cents. That's 0.60, right? It's the same idea. 100 cents on a dollar, 100 centimeters in a meter. You guys get that? So if you get a pendulum that's like 72 centimeters long, what number are you going to write right here? 0.72. You guys got that? All right. Next one. Angle. Let's go ahead and use degrees for a couple of reasons. One is that your protractors measure in degrees. And another reason is that when you guys do this calculation, as long as your calculator is programmed in degrees and not radians, then it's all going to be good. Run degrees. Okay. Now, there is last 2 columns of this table, which are both V. There are 2 different perspectives of V. One's the calculation and one's the empirical measurement. Okay. And I set up the calculation for you guys. I said V is the square root of. Okay. You guys know what goes inside that square root? It's this expression right here. Do 2 GL 1 minus cosine theta. Right? So you guys can calculate that, right? And of course, that'll be in meters per second because everything's in base SI units. True? Okay, you guys got that? Okay, and finally, the measured V, which will also be in meters per second. And this is straight off the speed gate. Okay. So again, get the thing swinging, hold the speed gate upside down, park it right here, let the mass swing through, and it, well, ideally it would register. I tried this over the weekend and it worked out really good. But I'll tell you guys what, here's the last tidbit I'll give you guys before I send you back to the lab area. Okay. Which is, this has not been very good at like picking up the mass swinging through. I don't know why. I tried like, well, maybe it's a materials thing. So I covered it in masking tape. That didn't help either. But it's really good at picking up your finger for whatever reason. So If it can't read this directly, what you can do is a proxy, which works pretty good, is like have this thing swinging back and forth, and then just hold your finger right next to the lab weight. Okay, so it's like side by side with the pendulum. Okay. And then go ahead and run your finger through this thing. Now, try it again. Okay. And it should tell you a number. Like in this case, 1.35 meters per second is what you just saw. Okay. Okay. You guys good? All right. So hold on. Here, try to get 3 trials. We got a solid 15 minutes in here, which is perfect. Then hold on to this paper because tomorrow, of course, we're going to be doing conceptual questions. Wednesday, we're going to be doing this lab, right? And then sometime later this week, we're going to finally finish this packet, which I'm going to eventually pick up from you guys as your homework. Okay, so you guys got that? All right, so everything you need is back in the lab area, and I'll be walking back there and helping you guys out.